we look at the properties and the stability of alkenes. And we know that alkenes have got a general formula CnH2n. When carbon atoms are 2, that would be ethene. If it is 1, now for alkenes, the number of carbons is supposed to start from 2. Because if you are talking about CH2 where you have got only one carbon, this alkene does not exist because you don't have any 2 carbons where the double bond is going to be found. So you need to have at least 2 bonds for you to have an alkene, 2 carbon atoms for you to have an alkene. So the general properties of an alkene, if you get to talk about the melting point and the boiling point. Melting point and boiling point gets to increase as molar mass increases. And the reason as to why you can talk about this is if you consider you have got these bonds between carbon atoms and hydrogen atoms. And when one alkene gets to interact with another alkene, because generally these are non-polar, the bonds that we are going to see are London dispersion forces. And London dispersion forces get to increase with increase in molecular mass. So when molecular mass gets to increase, the forces between the alkenes are higher. And because of that, it would take more energy for you to be able to break them, for you to melt them or to boil them. So that is why the melting point and the boiling point of these alkenes are going to increase in molar mass. Another property is solubility that you should be able to know. Now in comparison to alkenes, alkenes are slightly more soluble in water than alkenes. And that can be discussed because of the double bond which is found in these alkenes. So the double bond makes these alkenes to lack electrons, so they get to have a partial positive charge because of the double bond. We know that each carbon atom is supposed to have 4 bonds, but if we consider when you're talking about alkenes, let me say each carbon atom is supposed to be bonded to 4 different things to be saturated. But here it's only bonded to 3 different things. So it appears as though it lacks electrons. Because of that, it gains a partial positive charge. And that is what gives it a slightly soluble in water. Alright. So because when you get to consider this carbon that has got a double bond, it has only 3 things bonded to it, so the hybridization that it has is sp2 hybridization. And when you are talking about sp2 hybridization, the bond angle between the bonds is 120 degrees. So because of that, the bond, the geometry that we are going to be able to see in alkenes on the sp2 hybridized carbon is trigonal planar. We can also consider the stability, because when we are talking about these alkenes, you can have a group of an alkyl group being on one side of the double bond, and then you have got hydrogen on the other side. Or you can have the alkyl groups being on opposite sides, then you have got hydrogens on these other sides. So where the alkyl groups are on the same side, this one is called the cis isomer. When they are on different sides, that is called the trans isomer. Generally, the trans isomer is more stable than the cis isomer. We can see these R groups are further apart, and so there is reduced friction, we can say, or reduced repulsion. But when these R groups are together, they are more pushing themselves away because these contain electrons, and so electrons get to repel each other. That makes them less stable. So if we see this structure like this, this is not a cis isomer. We can see where the double bond is, for you to tell if it is cis, you need just on the double bond, you should be able to make a line, and then you are seeing these two on the same side. So these, if we make a line like this, these are not on the same side, so the line, you don't make it here. So this is not a cis isomer. We are just going to call this as a monosubstituted alkene. So this is the stability of trans and cis isomers. Now let's talk about the substituted alkenes. What would be their stability? So let's say we are supposed to have a carbon bonded to another carbon. Now instead of having hydrogen here, we get to substitute that hydrogen with a methyl. Now it might not just be a methyl. We can have even a butyl, an ethyl, a propyl, isopropyl. So let me just say R. So in that case, I'm going to just use a bond like this. Let's say we have got R here, we also have R here, we also have R here and there. So this one, we call it a tetra-substituted alkene because all the four hydrogens have been substituted by alkyl groups. This is the most stable alkene. And the one that gets to follow is a tri-substituted alkene. So you have got three hydrogen substituted, and then the fourth one is still there. The next one that is going to follow is a di-substituted alkene, where you can see two hydrogens like that and then two R groups. Now this is not a cis isomer. So from the di-substituted, we are now going to have the trans as stable. We know trans, the R groups are supposed to be on opposite sides like that. And then now we are going to have the cis. So the difference between this one and the cis, as we already said, for the cis, the R groups are on the same side like that. So after the cis, now we have got the monosubstituted, meaning that you only have one R group and then the rest are hydrogens. And then the least stable, when we're talking about alkenes, is a non-substituted alkene, where even this is going to be a hydrogen. That is the least stable. Now, why would this be the case? So this has to do with the carbocation that is going to be formed when a reaction is happening on this. So when you get to form a carbocation, meaning you get to form, let's say this bond is broken, and then you have got, let me give an example of this. This one gets a positive charge. We know that when you have got, let me give just something like this, you have got a double bond at this point. At this point, we have got one hydrogen and we have got two hydrogens here. So say we get to add one hydrogen at this point. So what is going to happen on the addition of an hydrogen here? This bond can no longer be like that because this carbon is going to have a lot of bonds. You can see 1, 2, 3, 4, and 5, and the carbon atom cannot have 5 bonds. So the result of that is that the double bond is going to be broken. So this double bond which was here is going to be broken. Remember, we have added now one hydrogen and we had done hydrogen here and hydrogen here. So what happens, because the double bond here has been broken, we can see this carbon which is here has got only 1, 2, 3 bonds. So it only has 3 bonds, and we can calculate the formal charge for this carbon. Formal charge is given by the valence electrons of the atom. Carbon is in group 4, meaning that it has got 4 valence electrons, minus the valence electrons which that atom is getting to have in that bond. So there is 1 electron from that bond, 2 electrons, 3 electrons. So we have got 3 valence electrons from this bond. So that will give us a positive 1 charge, meaning that this is going to gain a positive 1 charge. So this is a carbocation that is going to be formed with a positive charge. Now this one which is here, this carbocation which has been formed, is a primary carbocation. Why is it a primary carbocation? Because this carbon is only bonded to one carbon at that point. So if the hydrogen was added to this point, meaning that this hydrogen wouldn't be there, the carbocation would be formed here. And this carbocation is a secondary carbocation because it's bonded to two other carbons. And the secondary carbocation is more stable than a primary carbocation. And the reason for that is that there is going to be a sharing of this charge that has been formed by this carbon and this carbon here. When you only have the carbocation formed by the primary carbon, the charge that is going to be formed at this point is only going to be shared with this carbon. And so that is why there is more stability for this one in comparison to this one. So basically what we are saying is, when you consider the double bond, the more the R group on the double bond, the more stable that bond, I mean that alkene, is going to be. Let's consider these questions. Consider the two alkenes. We have got 2-methyl-1-pentene and 2-methyl-2-pentene, and decide which would be most stable. So the first thing is we should be able to draw the structures of these compounds. We can see both are pentenes. First carbon is going to be here, carbon 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So for this one, the double bond is at carbon number 1, we can see. So we're going to put a double bond here, and then the methyl group is at carbon number 2, so I'm going to put a methyl there. For the other one, the double bond is at carbon number 2, so this is carbon 1, carbon 2. So the double bond is going to be here. The methyl group is still at carbon 2. It's there. So from what we are able to see, which one is going to be more stable? So we're going to consider how many alkyl groups are on the double bond. So we can see this is the double bond at this point. So if we see we only have this group and this group bonded to the double bond, so we only have two alkyl groups here. If we consider where the double bond is at this point, we have got this group, and this group, which are directly linked to the double bond. So we have got 3 alkyl groups. So where you have got 3 alkyl groups, we expect it to be more stable than 2 alkyl groups. So it is a tri-substituted alkene. So it is more stable than a di-substituted. Let's consider this one. Rank the following cycloalkenes in order of increasing stability. If we consider the first one, how many substitutions do we have? So you can see to the double bond, we have got 1, 2, 3, 4. So we have got 4 alkyl groups. For the second one, this is a double bond. We have got 1, 2 groups. So we only have 2 there. If we consider the third one, this is the double bond here. The groups we have got 1, 2, and 3. So we expect that the most stable is the first diagram, followed by the third one, and then the second one. So that would be the order of stability. Let's consider also this question. Heats of hydrogenation of 3 alkenes are as follows. So hydrogenation is simply the addition of a hydrogen. So I've got 2-methyl-1-butane is negative 119, 2-methyl-1-butane, 3-methyl-1-butane is negative 127, and 2-methyl-2-butane is negative 113. Write the structure of each alkene and classify it as to whether it's doubly bonded atom, monosubstituted, disubstituted, trisubstituted, or tetrasubstituted. So let's start with all these are butanes. So first I'm going to put 1, 2, 3, 4. If we consider the first one, the double bond is at carbon number 1. So we'll put a carbon double bond here. And the methyl is at carbon number 2. We consider the second one, double bond is still at carbon number 1. The methyl is at carbon number 3. Consider the third one, double bond is at carbon number 2. the methyl is also is carbon number 2. So there. Now let's classify them. Are they going to be monosubstituted, disubstituted, or trisubstituted like that? So if we consider the first one, on the double bond, how many groups do we have? 1, 2. So we only have 2 groups, so this is a disubstituted. If we consider this other one, the double bond is here. How many groups do we have attached directly to the double bond? We only have 1 group. We don't consider the hydrogen. So this one is a monosubstituted. Consider the third one. 1, 2, 3 groups. So this one is going to be a trisubstituted. For question B, write the structure of the product formed when each alkene is hydrogenated. So what happens when you get to add hydrogen to these compounds? That's they're hydrogenated. So what we are going to see if we get to react with hydrogen is that these, when alkenes are added to hydrogen, or hydrogen is added to alkenes, the double bond is going to be broken. So what gets to happen is that these get to come and break this double bond which is here, and so you are going to form the equivalent alkane. So what are we going to have here is that the double bond is going to be broken. Then you are going to have like that, because these 2 hydrogens are going to come and attach to this point, and we know that when that happens, actually 1 hydrogen is going to, because we already have 2 hydrogens here, and for this one, 1, 2, 3, 4, we don't have any hydrogen at that point. So this is what we have. So what gets to happen is that from these 2 hydrogens, one is going to come and attach here, one comes and attaches here. So the double bond can go nowhere, and we're not going to form any carbocation here because everything has been balanced. So that is what gets to happen. For the second one, again, when you get to react it with hydrogen, the double bond is going to be broken. So what we are going to have is this. The third one, also the double bond gets to break. What we're going to have is this. So all these compounds, if we can notice, they are all the same. Because if we count for the first one, this will be position number 1, 2, 3, 4. Position number 2, we have got a methyl. If we count the other one, we'll start counting from here, because that's what will give us a group, the smallest number. It is 2 at carbon number 2, even this one. So the result is all the same. Right. So write the structure of the product formed. These are the structures of the products that are going to be formed. C. Can heats of hydrogenation be used to relate the relative stability of these 3 alkenes? So these heats we are seeing here, are we able to use them to determine which one is the most stable? Actually, yes, we can use that, and the reason is because we are forming the same product. Since we are forming the same product, we can actually just get to use their heats of hydrogenation. Okay. So if so, what is the predicted order of stability? If not, why not? So from the heats of hydrogenation, we expect that the most stable is going to be this one. This will be the first. The second one is going to be the second, and then the next one is going to be this one. So we're going to start with the third one, followed by the second, and then the first. That is from the heats of hydrogenation. And the reason for that is the smaller the heat of hydrogenation, the more stable. It's like you are easily able to add an hydrogen on this compound. So the more easy it is, the more stable. So that is what we are able to determine. I think we are able to deduce from the heats of hydrogenation. Or maybe I followed the values wrongly. So we're supposed to get the smallest value and then the next. Which one is the smallest value here? So if we consider this one, negative 113, negative 127, negative 119. Which one is the smallest? So from the stability here, the most stable is going to be this one, followed by the first one, and then this one. Okay, like that. So what we're able to determine the smallest actually heat of hydrogenation, when you get to have a very big value, that is going to tell you how stable it is. Okay, so negative 113 is bigger than negative 119. Negative 119 is bigger than negative 127. So this one is going to be the most stable because it has got a higher heat of hydrogenation as compared to these others. The thing is this one, because it has got a higher heat of hydrogenation, meaning that the way it is okay for you to be able to add hydrogen. You are going to release more energy. So because you are releasing more energy, just think of it: when you are running, you are less stable than when you are walking. The reason is you are releasing more energy when you are running. So same here, you are releasing more energy when you're adding hydrogen, so that makes it less stable than this one, which is getting to release less energy. Because we know that for negative numbers, the bigger it seems to be, the smaller it is. Okay, so that is it. So the order of stability, the first is this one, followed by this one, and then this one. For E, what other alkene isomers, or maybe we can even get to use just what we know to determine the stability. Instead of using these values, we can use the structures. We know that a trisubstituted is the most stable, followed by a disubstituted, and then a monosubstituted. So even from what we know, we are able to determine that. So for E, what other alkene isomers are possible for these alkenes? Write their structures. So what other alkenes are possible, the isomers possible for these ones? So we can see all of these, they've got, let me just get to remove this. All of these have got 4 carbons, and they've got a double bond somewhere. So we can actually just get to rearrange the double bond, then that is going to give us the isomers. So one of them we are able to have, we have got 4 carbons, 1, 2, 3, 4, like that. So this double bond, we can as well get to bring it on the middle here, like that. Now notice we have got 1, 2, 3, 4. But what of the methyl group? Where is it going to go? So the methyl group, we can actually bring it at the end there. So that is going to be one of those isomers that we are able to have, where we take the methyl group at the end. Or we can as well get to have, this one is going to have 5 carbons, and then the double bond is going to be somewhere here. Okay, so for this one, the double bond is on the second carbon, or the double bond can be on the first carbon. They are generally the same. This one and this one are the same. It's just that the double bond's position is different. Or we can have a different one. So this one, if we want to name it, we can see this group is down, this one is on top. So this one would call it as a trans. We can also have what is going to go like this. So you can see the two groups are on the same side. This is going to be the cis. It's also an isomer, just the same like this one. It's just that this one is a trans. Also this one has got 5 carbons. So these are the possible isomers that we're able to have. What are the relative stability among just these isomers? So what would be the stability of these isomers that we've written here? Now from what we are able to deduce, this one is going to be the least stable. Why? Because it is a monosubstituted. So this is going to be the third one. And we know that generally the trans is more stable than the cis. So that would be the first, second, and then third, like that. Okay, let's consider this as the last question. Predict the most stable alkene of each pair. The first pair, I've got 2-methyl, 2-pentene, and 2-methyl, 2,3 dimethyl, 2-butene. Let's start with the pentene. got 5 carbons, 1, 2, 3, 4, 5. And then the other one is a butene, so 1, 2, 3, 4. So this one is 2-methyl, meaning at position number 2 I've got a methyl, and then 2-pentene. Position number 2 I've got a pentene. The other one is 2,3-dimethyl, so at this position I've got a methyl, even here methyl, and then 2-butene there. So which one is going to be more stable? So this one has got, it's a tetrasubstituted alkene. This one is a trisubstituted. So we expect that the second one is going to be more stable. This one is going to be the first, and then followed by this one. Let's consider the next. Cis-3-hexene or trans-3-hexene. Now, we already know that the trans is going to be more stable than the cis even without writing the structure, because it's the same compound, it's O3-hexene. So the trans is going to be stable. For C, we have got 1-hexene or cis-3-hexene. So hexene has got 6 carbons, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So for the first one is 1-hexene. The next one is cis-3-hexene. So 1, 2, 3. So I'm supposed to have a double bond here. But because it's cis, meaning that these are supposed to be on the same side. So I can also write it like this. So this is a cis-3-hexene. So which one is going to be more stable? So from what we are able to see, this one is going to be more stable than this one, because this one is disubstituted, and then this one is monosubstituted. And actually we also know that cis isomers are more stable than monosubstituted isomers. And then the last one, we are talking about trans 2-hexene and also the pentene. So 1, 2, 3, 4, 5. Trans 2-hexene, meaning that the position of the double bond is position number 2 there. So you can rewrite this to make it a trans. So we're going to have a double bond here, and then we're going to have 1, 2. I can put it like this. Okay. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So just to make sure that the groups are on opposite sides, that's why I've written it like this. And then we have got the 2-methyl, 2-pentene. So which one is going to be more stable? So from what you're able to see, this is a trisubstituted, and then this is a disubstituted, even if it is a trans. So a trisubstituted is more stable than a trans isomer. So this is going to be more stable than this one. So that is it for this tutorial. Thank you so much.